Okay, welcome everyone back for the second session of today's masterclass. We will resume the talks with an EGNOS overview that will be given by Javier Andrés Diaz. Javier Andrés Diaz works at ENAIRE at the ENSAT department, and he's been very kind to give us the next talk. Let me introduce first the speaker. Javier obtained his Master of Engineering in Aerospace Engineering at Polytechnic University of Madrid in 1992 and obtained in the same university a Master in Space Technology in 2009. He joined INECO in 1998 and worked since as a technical assistant for ENAIRE Satellite Navigation Department. For 5 years, he joined the ESA Project Office for EGNOS in Toulouse. Since he has been working in ENAIRE on the use of GNSS for aviation, mostly involved in research projects for novel applications and supporting tools, in international standardization groups, and in the provision of aviation user point of view on the definition of GNSS systems evolution. So, Javier, the floor is yours.
Okay, thank you very much, Adrian. Good morning, I think good morning for you, or perhaps good afternoon, not sure. As Adrian said, I am an aeronautical engineer, so perhaps already a colleague or very soon colleague of yours. I've been working since a very long time in the GNSS business, and basically, well, oriented to aviation, as in this case, it's linked to my career, engineer in aerospatial. I will introduce you, provide an overview of EGNOS. It will be more oriented to how EGNOS is seen from the aviation perspective, which is my main experience. I thank you for your attendance. I hope you will find it interesting. Okay, so the content of the presentation it's have 6 parts. First, I will give you a very short introduction about ENAIRE, so that you can have a view of where my experience comes from for what I'm going to tell you afterwards. I will provide them an overview of the EGNOS system and services, this European system, together with Galileo GNSS system. Then I will tell you about why we are interested on EGNOS in aviation. Afterwards, how we use EGNOS in aviation. Then some examples of benefits that we are getting with EGNOS, concrete examples, and also some precautions that we are having to have in order to use EGNOS to be sure that it fits our needs and to kind of monitoring, let's say. And finally, I will tell you about the future of EGNOS evolution that is already being prepared, and quite soon we will have it with new services. So ENAIRE is a Spanish public company. It depends of the Ministry of Transport. We are a leading air navigation service provider. We provide aeronautical information in Spain. We also provide air traffic control in both en route approach on aerodrome airspace, together with flight information, alerts, and also consulting service. This is the kind of services that we provide. On top of that, in order to support the transit and the flights over the airspace that we control, we provide communications, navigation, and surveillance services all across the whole of the Spanish airspace. In the picture above, just beside the logo of ENAIRE, you can see Spain, which is the Peninsula, and Balearic Islands and Canary Islands. And this sphere area is where we provide some ATC services and information services. It's a quite extensive air space. We can consider ourselves as pioneer in the use of satellite navigation among the air navigation service providers. What we use in aviation are GNSS together with augmentation systems, which can be AVAS. It's an augmentation system which is on board, directly on board the aircraft. So the SBAS is the, like EGNOS we are going to talk now, is the satellite-based augmentation system. The GBAS, which is the ground-based augmentation system. And we are using this satellite navigation quite well, we will say, it also supported by the extensive experience we're having with other, let's say, conventional navigation service provision. We participate also in many international groups, which deals with several different GNSS matters, of the technical matters and operational matters. Technical, like standardization of, for example, onboard equipment, regarding robustness, so how we can protect this GNSS service from, let's say, for example, in radio frequency interference. We also provide our expertise view about what evolutions could be beneficial for the use of these systems, in particular for aviation. And then we also participate in groups in which we discuss how we better use these systems. How do we implement operations? We choose these systems, and how do we relate with the service provider of systems services like EGNOS itself, and etc. We implement what we call PBN, performance-based navigation. I will explain later on a bit more what is this about, but it's one of the main benefits that is provided by the use of GNSS. Then, in order to use this different GNSS augmentation system and the core constellation themselves, we need to ensure that the performance they are providing are adequate, and we must make sure also that there are no problems that are caused by, for example, interference sources on ground or not on ground, from whatever they come from. So we have also deployed a network of stations by one hand for the monitoring the GNSS performance, on the other hand to detect and localize these interference sources for GNSS. So the first one is called RecNect, and the second one is made up with what we call our dilemma systems. On top, you can see a picture of one of the monitoring stations of the dilemma, with which we can get the bearing from which the interference source is. And then with several of these stations, we can afterwards do triangulation and localize where the source comes from, and do the necessary to find it completely, to identify the source and to cancel it with the help of some other authorities. Then we are also about all this satellite navigation. We provide ourselves a satellite navigation service, which is a GBAS, ground-based augmentation system service, which enable us to have precision approaches supported by this system, GNSS system. And you can see here in the picture on the top right, a scheme of how this system works, the architecture, let's say. So you have several monitoring stations. They are close to the runway where you carry out the precision approaches. Typically, there are 4 monitoring stations. They receive the GNSS data, then send the raw data to control stations, where it compute what are the errors that are in these signals, are receiving these signals, the errors that are created in the measurements, and then it transmits these appropriate corrections and information so that through a VHF antenna to the users, to the airplanes that use this information to get a more accurate position and also to have integrity information, which is vital for in aviation, so that they can carry out, in this case, precise approaches. Here below, you have some of the elements of GBA systems. You have a typical antenna of the monitoring stations, monitoring antennas. So you can see, for example, that it is, well, as you can see, it's not, I would say it's not a typical GNSS antenna, but it's very much protected in particular against multipath and is very well, let's say, calibrated to have, for example, this amount of stones around it. And this it has been found that it's a very good way to prevent multipath. You have central stations, which is at the end is a typical rack, but you have the computers, and the important is those algorithms. There are also, of course, many auxiliary systems that ensure that all the system itself functions at adequate temperature, and that you do not have cut-off power, for example, because this is a very important system. And here at the right, you have a typical antenna. The antenna, in fact, that we have already deployed. This is in Malaga Costa del Sol Airport. You can see it's quite big and high. You can see a little person there. So on top of that, we host and we provide part of the operation of the EGNOS system itself, because we have one of the EGNOS control centers. It is located in Madrid, and so we provide the person prepare and train to operate the system. In this way, we contribute to this the provision of the service. And on top of that, we have what the monitoring stations of the EGNOS system that afterwards we will show you in architecture scheme. So we have about 5 of them, when we have in total around 40, all distributed in Europe and outside Europe. So that's for EGNOS. So sorry, for ENAIRE. So as I said, we are a navigation service provider. We benefit and we use GNSS systems to support several of our implementations. And afterwards, we will tell you how we do it. And on top of that, we use other augmentation systems that are the ones used in aviation. So let's see about EGNOS. EGNOS stands for the European Geostationary Navigation Override Service. It is a system that is owned by Europe Union. It's the European SBAS. So SBAS is satellite-based augmentation system. The satellite-based augmentation system, they all follow a standard in what the production of the signals they are transmitted and used by the users. And this system provides both a positioning and timing service that are so not only positioning, but the timing is also very much used in aviation, and more each time there are more systems in aviation that use the timing provided by GNSS because of the advantage that you can with just a receiver, you can have it everywhere, and you have such very precise timing and synchronized. So as we say, this is a satellite-based augmentation system. There are 3 kinds of augmentation system: the ABAS, the SBAS, and the GBAS. ABAS is the airborne augmentation system. So this has the advantage that wherever you go, you have the augmentation system with you. So it allows to have an augmentation service which is global. So it has a very good advantage that. Then we have the SBAS EGNOS and the SBAS service, which is provided through satellites, and it provides at the end a service which is regional. And finally, we have the ground-based augmentation system, and as you can imagine, is local. So each has their advantages. What I would say is that the more you have a smaller service area, the more precise that you have on the service. So I would say that with the ABAS, you support some operations. With SBAS, you support more stringent operations, and with GBAS, the most stringent operations. So that's why all of them are interesting, and they are, let's say, in some way complementary. Okay, coming back to EGNOS, there are three core services. The open service. This is a service which is free, and it's what it does is improve the position accuracy to within 1 to 2 meters 99% of the time. So this is important. This 99, because it's not only that you get a good accuracy at a certain moment. No, we do not. The interest is that it's quite permanently most of the time. So this 99%, it's the one that determines when you have a long time period measuring the system, then you can see what is the best accuracy during the best, no, the accuracy that you at least maintain during such a long time. Then on top of that, we have the safety of life service. This is the one for safety critical transport applications like aviation. And they require both an improvement in the performance, which must be improved, but also warranty some way. So it's, we need to have it permanently. And also what we can say, an integrity warning system. We must know at all real time if the system is provided, is performing as the service is defined, and we must know what is the integrity provided by, which we will see later, is what is the maximum error we could have. So if this maximum error overpass one threshold, then we have an alarm. And finally, we have the third service, which is what is called the EDAS, the EGNOS Data Access Service. In fact, in this case, what you have is the data transmitted by the satellites. You have this data transmitted via internet, which is very much interested to other people for other kind of use. So, for example, for a university to do research about it, and for example, if they want to get this data somewhere which is not under the SBAS broadcast area. So the communities, so I will provide here more the perspective of the aviation, but the user communities of EGNOS is very broad, it's very big. So aviation first, you will have also agriculture. Agriculture, for example, they are mostly interested in the open service. There's no need, it's not a safety critical application, let's say. Maritime is also safe critical. Then you have surveillance. You have the rail, which is also a safety of life service. You have the location-based services, as you have in your mobile device. For the road, for the timing. So as you can see, many user communities. And EGNOS is one of the SBAS systems in the world. You have several ones more. You have in America, you have the WOS. In Russian, you have the SDCM, SBAS system. You have also a South Korean one, an Indian one, a Japanese one, and other ones that will soon we will have also additional ones. As we will see afterwards, the idea is that we have enough SBAS systems that at the end we practically cover all the Earth's surface. That could be the interest of it. So regarding the EGNOS Safety of Life service, this is available already from 2011. So it's already some time ago. It's performing well. No single integrity failure. And it's very good availability, and so we are using it each time more and more in aviation. The EGNOS service enhance or augment one of the core constellation services. And in the case of EGNOS, is the GPS standard positioning service, which is obtained using the GPS L1 course acquisition signals. What this enhancement, this augmentation by SBAS gives a status of the GPS satellites, health status of the GPS satellites on quasi-real time, so that the users, if there is a GPS satellite which is not in good health, it excludes it from the position computation. And it is, to clarify, so you have the GPS system itself also protects itself. So it has a monitoring of itself, and the GPS satellites will say when they are not okay, so telling you don't use me. But this health status actualization is not so quick as it is provided by EGNOS for services which require quasi real-time information regarding this status and integrity, in fact. So finally, so it provides also corrections for the ephemerides and clock information provided by each of the satellites. On top of that, it provides also corrections for the ionospheric delay that is provoked by the ionosphere in the signals transmitted by the GPS in this GPS L1 CA signal. And this ionospheric correction is provided via geographical grid points. In the picture here, you can see these grid points which are plotted some way over the Earth's surface. Depending of its color, it means that it's providing information that can be used to carry out these corrections in the ionospheric delay. When it's gray, it could mean that it's not providing information. So you have also the satellites. If the ones which are in green color, it means that you are having information from SBAS augmentation. So you have information about his health status and also corrections about the ephemeris and clock. And altogether allows to improve the positioning and timing service. So on top of these corrections, what is important for the safety of life service, you get information with which you can compute bounds to the residual errors from these source errors. I mean, from the errors in the ephemerides and clock of each satellite, and from the errors provoked by the delay that caused the ionosphere. So with the information provided in the EGNOS signals, you can see what would be the maximum error after these corrections are applied. This augmentation data, as I said previously, it's broadcast timely through geostationary satellites, and is broadcast in a GPS L1-alike signal. This allows to have a similar, let's say, hardware components, the same receiver components that are used to receive the GPS L1 signal are used to track and process the geosatellite signals of the SBAS system, which is a good advantage. As you see previously, in the case of GBAS, ground-based augmentation system, the option has been another to transmit these corrections through a VHF antenna. So you must get it through another unit, let's say, on board the aircraft that transmit afterward this information to the GBAS equipment. What is the architecture of EGNOS? You have a picture here. So you have a network of monitoring stations. They receive the signals from the constellations, core constellations. You can see double lines. Why? Because we receive not only, and we process not only the GPS L1 signal, but we process another signal which is in another radio frequency band. And having both of them, then this allow us to get information about the iono-provoke delay in the signals in GPS L1. So it is these signals give us information to afterwards compute the corrections in the GPS clock and ephemeridess, but also allow us to get information about what is the EGNOS, how the EGNOS is provoking delay in the signals from these core constellation satellites. So, okay, all this information is go to a center, processing center, and once the corrections and integrity associated information is computed, then it sends to a application station that sends to geostationary satellite, and it transmits to the user, in this case an airplane user, a space user, that receive at the same time the signals from the satellites of the core constellation on the GEOs. So this network of stations are called RIMS. There are 2 mission control centers, and we use 2 or more GEOs. Why 2 or more? Because in order to ensure availability at any time, so and you always anything always can happen. Something can't happen. You lose a GEO satellite, and you have still a second one to keep maintaining the service. You can see in these pictures, which is the distribution over Europe of the RIMS locations, and most are in Europe, but some others are on Africa, some others are even in United States and Canada. And then we have a very important part, of course, of this service, which is the user equipment. Without the user equipment is the one that must know how to process all this information. Then the user equipment gets this information of corrections, and then computes the timely, what is the position and time, improve in accuracy, plus they compute what we call the vertical protections and horizontal protection levels, which provides the safety of life service. With this protection level, as you can see in this picture, this airplane in the center, so you let's say you get this position with the system, with the GPS plus the EGNOS provided information, and then you have this protection level, and you can be sure that the aircraft must be within this cylinder, let's say. And if this cylinder is adequate for the operation you are going to carry out, then you can continue. Otherwise, you must abort or use another system. So in order to compute this protection level, you do not only use this information provided by EGNOS, which is allows you to bounce the clock, ephemeridess, and EGNOS provoke errors, but you also have other models inside this equipment, receiver user equipment, in order to bound the errors which are due to noise, to multipath, to troposphere, to satellite geometries, etc. So you have a final protection level. In this picture, you can see that you have, this is based on that you have an alarm limit. In case these protection levels is higher than that, bigger than the alarm limit, in that case, then you lose, it triggers, the user equipment triggers an alarm, and then the user knows that the system does not support the application it's using. So these protection levels are computed with a confidence level adequate for the safety of life application. And as I said previously, so each safety of life application has their associated alert limits, which are compared with the protection level. For example, here we are seeing a vertical alert limit. So we compare it with the vertical protection level. Well, the vertical protection level is below this vertical alert limit, the service is available. At the moment that it's bigger, is higher than it, then the system becomes unavailable. And that's the way it works. So this is pictures which gives the progression of the protection level in time. One thing which is important for later use of the EGNOS is to firstly to know that it's used the signals that are broadcast, like all the other ELVA systems used in aviation. It's compliant with standards, and that allows that all the equipments which are on board the aircraft know what signals they must receive and use it. It's typical standard stuff, as you know. And then we have, I would like to point you about, we have several EGNOS areas. We have what we would call the geosatellite coverage area. is all this area over the surface of the Earth where you receive the signal, but the fact of you receiving the signal is not that because of that you do not have the service. You need to be inside what is called the commitment area. So you can see here, which would be the area where you will receive the signal from the 2 GEO satellites, geostationary satellites that are being used currently by EGNOS, but the service is only provided in this commitment area. And then this commitment area is a long-term confidence that the service provider has about what would be the provision of for what applications, for what service level they will provide, where you can use it. Other thing is in the real time, which is this later picture. In the real time, the performance can vary. So in some cases, you may have a picture of what is the service availability is a bit lower than this one, but most of the time, of course, this is the commitment area, would be bigger. But this at the end, the service of the EGNOS service is an augmentation system of a core satellite constellation. If there are problems in the satellite core constellations, for example, there are some GPS satellites that become unhealthy, which was not foreseen. This may provoke deterioration in the service provided by EGNOS. Let's come now to why EGNOS is interest for aviation and in general, let's say, in GNSS. So firstly, know that EGNOS was designed for aviation. So many, in particular, for example, in ENAIRE, we put money for the development of both the ESVAS standard and the EGNOS system itself. Well, the ESVAS standard it's something done by the aviation community, but we participate on that. But we put money, we were investors in this EGNOS system and service because we wanted it because it was interesting for us. And EGNOS is interesting for aviation also because they use a terrestrial reference frame, which it means that the compute position put us on over the Earth using a reference, and which is the one is similar, or almost equivalent to the one adopted by the civil aviation community, which is the one used by GPS, and is so much equivalent that we can use it directly. Furthermore, the EGNOS system is certified for civil aviation in Europe, so it means that it has been assessed that the system has been developed with the necessary quality and is performing as designed and in compliance with the standards which are required in aviation. So PBN, I told you about the performance-based navigation, that it was of so much interest for us. So here is the way we were flying. We fly in aviation. When we use a conventional navigation system, we must fly from one flying over the different navigation stations. We must go. We cannot design any kind of desired path. We must go over them, and then we have a limited flexibility. This same trajectory, when we have we start applying performance-based navigation, thanks to the what we call area navigation method, we can decide that instead of going through these, let's say, these lines which are cutting one to other, we can have some more, let's say, more fluid or more efficient trajectories. And this is with this area navigation method. And then we have the RMP and this radio require navigation performance that it allow us to optimize more this navigation method, area navigation method. And this is provided thanks to augmentation system. The augmentation system, firstly, they increase the accuracy of the position, and on top of that, they provide us integrity information about it. And then we know, let's say, think about that the aircraft is following this route, and we have this let's say it's like a kind of road in the air, and we know with this information provided by GNSS where we are in this road, and we can be sure that we are not outside of it, this, let's say, motorway of the airspace. So GNSS, and in particular EGNOS, is an enabler of the PBN, and EGNOS in particular allow us to provide this kind of navigation from en route down to precision approach operations. So during all the phases of the flight. EGNOS supports all the phases, and these are supported via three services that are provided: the MPA service, the APB1 service, and the LPB200. And this is thanks that the position that is provided with GPS plus EGNOS allows to cover these the requirements for these services, for these operations. So it's a regional service, but as you previously, it's a standardized, and this allows them to a user for use the different airspace service along the over the Earth. It's why is interest for aviation for it's regional, and then and it allows to have approaches with vertical guidance. Let's say three-dimensional approaches, and these enhance safety. This increase accessibility because of the vertical guidance. This increased the accessibility due to lower minima. You can see in this picture, when you have a non-precision approach, you must fly at certain moment. You must start flying horizontal, and then until you see the runway. In the case of you are doing with vertical guidance, you can go all the time descending towards the runway, and then what you have is a kind of decision height, and then this decision height is usually much is lower than the minimum descent height that you get with non-precision approach. And then if you have, for example, clouds, for the user using a non-precision approach, he will not see the runway, so he will not have access to it. He will have to divert and go to another airport. But the one using this approach with vertical guidance could go closer to the runways and then have good visibility of it, and then carry out the landing. And so it increased accessibility, and well, furthermore, it's also backup of other conventional systems that allow this kind of precision approach. You can see here, to give you an idea, the deployment of the kind of LPB operations that this is what we call LPB200 in this case. And these are vertical guidance down to a minima of the type CAT1, which is a precision approach, let's say. And so you can see that we are deploying many of these type of operations. And what is very important, and I forget about telling you, is that there is no need of costly ground infrastructure, because the service is being provided regionally. So we have this, what you saw previously, this network of stations, and we have a central facility, and then we have the SBAS geostationary satellites from which we broadcast. We do not need to implement any other part of this system on each of the airports here, runways. We do not need to install any of them. If the runway has the capacity to allow precision allow approaches, and then they can implement it. So with a single system, we have many precision approaches for all over Europe. So it's great. Obviously, you must these service approach implementations are carried out in the area where the service is provided. In this case, is the red one, as you can see, is the one that provided LPB200. And then there are other vertical guidance, which is less, which does not allow to descend to a decision height so low, which is the APB1. APB1 and LPB200, they are similar, let's say, services. They both provide vertical guidance, but the second one allows you to descend more near to the airport, to the runway. Still, this advantage, it allows us to improve air navigation concepts, to have, this is an example of this kind of improvement. So typically, well, this you follow the conventional navigation signals to get to the airport. When you apply improved navigation services, you can create horizontal procedures which are more close to the runway, which are more predictable. In the case you can be sure that all the aircraft follow the same trajectory when they use RMP, and this is very helpful for the air traffic controllers, and also you can short the trajectory flow, and so on. So there are different concepts about that. It allows us to rationalize some of the conventional systems, and it's also a source of information, of position information, for what is called the ADS-B system, which use the position computed by the aircraft to transmit it to the air traffic controller, and like if to tell them where they are. Must go a bit quicker, I think. How we use the service in aviation. So first, the service must comply with the aviation standard, ICAO SARPs. It may happen that they not achieve exactly completely some of the performance requirements, and in this case can be some waiver. What is requested by the SARP is in terms of accuracy, integrity, continuity, and availability service. So here you can see that we are talking about an accuracy of 16 meters for horizontal, 6 meters to 4 meters for vertical. You can see here a time to alert, which is the time within which you must tell, you must have a warning in case something doesn't work correctly. You have also requirements about the continuities, which is the probability of that once you have started an operation, you have to interrupt it or not, and you have percentage of time in which the system must be available. So there is a service provider that provides this service, which is the ESSP. This is the logo, and must be also certified by aviation authorities. Between the air navigation service provider and the EGNOS service provider, then there must be EGNOS, a working agreement, so that they receive timely information if there is any problem with the service provider. So as it's time, they can notice or advert or give information to the users. I think, and of course, the equipment used by the users must be also certified. In the future, the use in aviation, so we intend to use it for the navigation. So we have in that case precise trajectory, but also timing while flying, navigating. So we want the aircraft to pass over a point at a precise moment. It will be used to support non-demanding operations. So lower minima, being able to descend more close to the airport runway before needing to have visibility of it. And also it could be a solution that is being studied for the unmanned, for the UAS, or Airbus, is unmanned vehicles. And so some examples of benefits. So you can see here, we have implemented an operation with EGNOS, and this is the altitude at which the pilot of the aircraft must see the runway in order to be able to proceed with the landing. And you can see that with this conventional system, it's you are over 1,300 and 700, and well, once you get EGNOS, you get as low as, in this case, as 328 feet over the runway. And then because of these good procedures that they are more flexible, and they allow you different to shorten, for example, the approach trajectory length, and also to avoid flying over some population areas. But you can get benefits regarding the emissions and also about the noise area. But there are precautions to be taken into account. So we must continuously be sure that the services are being provided adequately as they support the operations for which they are being used. And then we must monitoring this GNS service and warn aviation users and air traffic controllers when they are not met. This is done via what we call NOTAMs. So because of that, as I told you, we have a network of stations to doing this kind of monitoring. And on top of that, we have also real-time information in the case of EGNOS provided by the EGNOS service providers. So the signals of GNSS are protected internationally, but they are easily jammed. As you know, they are very low. They have a very low power, and then they are easily jammed. Interference is quite easy. So this interference can provoke service degradation and even service loss. And so because of that, we have this network of monitoring stations and also this interference detection and localization network. Here you have a picture which is provided I think both in the standard documentation, in the one for the equipment and the one for the system, in which tells you what is the interference environment which is susceptible for the system. And you can see here that we are speaking about interference of the level of minus 120 dBm. So as you see, it's really weak signals, and then we must protect it. So of course, there are precautions. Why? Because they are dependent on GPS constellations. Nowadays we have around 32 GPS satellites operating, but it's not guaranteed they are all the time there, and could be reduced. The warranty is about 24 satellites, and so this reduction can provoke a degradation in the service finally provided by EGNOS, because EGNOS is based on the use of GPS. And then we have another precaution to take into account is that it's space weather, and there are, in particular when there are solar peaks, they can provide disturbance of the in the ionosphere, and this can provoke degradation and even loss of the service. That's why that's being this is more and more taken into account under ICAO. There has some global space weather centers services which publish advisories about the potential impact of the service. EGNOS evolution, EGNOS natural evolution, and I guess that you have read about that, is that the user level will use double frequency. This is certainly great because it removes one of the big source of errors, which is the delay provoked by the ionosphere. So we get iono-free measurements. And also, EGNOS will use not only dual frequency, but multi-constellations. In fact, EGNOS will use in the future both GPS, will provide augmentation both for GPS and Galileo satellites. It means that the EGNOS user will be able to use not only the GPS satellites, but also the Galileo satellites. And so they will have additional satellites and even additional constellations, not only one constellation. So the performance will be better, as I said, free of ionospheric errors and better satellite geometry. And the robustness, of course, will be better. So could not be impacted by ionospheric scintillation, will not be impacted by a single constellation failure. It will be difficult that you will have in a poor satellite geometry situation, because there are so many satellites that can be used. And also a very good advantage expected, and could be an increase in the service area. So in this picture, you can see the blue one area. This is the one currently provided by EGNOS, let's say L1, single frequency GPS, augmenting GPS L1. And you have two additional service areas. The orange one is the one expected to be the service areas when you use double frequency plus one of these constellations, GPS or Galileo. And when you will use both constellations, two constellations, it will be even increased. And so you can imagine that then with WOS will also progress to a double frequency service. So in this case, the service provided by the SBAS systems deployed in the world, they overlap, and then the SBAS user will have a continuous SBAS service, which may allow them to carry out precision approaches. And that's all. Yes, I passed a bit, the 45 minutes. Thank you very much for your attention. Obrigado. And please, any questions will be welcome. Thank you very much.
Okay, thank you very much, Javier, for this very nice presentation. We have time for a little bit of questions before we go for lunch. I have myself first a couple of questions. On the previous slide, when you were mentioning the evolutions, here I assume that is without deploying any new satellite or ground infrastructure. So taking EGNOS as it is, or these extension maps, they assume more ground stations or more satellite links?
Yeah, this is a very good question. So firstly, I would like to come back to one picture on the architecture of, yeah, you can see here in this picture. So we used the two signals from each of the constellations we are monitoring, each of the satellites, to have a monitoring at the same time to compute the ionosphere delay. And so you can see that the network is quite dense in this case, as you can see for what is the EGNOS current service, because we need to have very much a lot of information from for the IONO to get this to be able to provide this precision approach support this precision approach. Once you do not need to provide this information about these corrections for IONO, in case the users are using double frequency, so IONO free, it means that you do not need so much RIMS network, so a dense RIMS network. It will be the RIMS network will be then only used to monitor the satellites, and the satellites you will see them from. I mean, in that case you could reduce this network of RIMS, and what you will do is, in fact, probably will have RIMS more far away from where. And there would be no group, and you could take them more far away, and this will provide you. I mean, the point is to have these satellites monitored as soon as possible, and to have these satellites monitored, you must they must be seen from a minimum number of RIMS station, of monitoring station from the system. I think they're satisfied by the answer.
Yeah. I think it's around 3 RIMS station need to monitor one satellite. But then we need to deploy more stations in Africa, in the African continent.
I guess yes, it will be like that. I mean, you can see here you have some RIMS stations which are quite far away. You can imagine that you will have to deploy some of them. Probably it could be of much use if they are deployed. I mean, the more you are occupying a more vast area, so you will be able, in that case, to have. If you want really to have this extension, if you want to monitor satellites which are providing, which are seen by this user, then you better have monitoring station near this user.
Okay, so I think we have time for one quick question from the audience. So you can come closer.
Can you listen to me?
Yes.
Hello?
Yes. Okay.
I'm a little bit surprised. Please let me know if I'm wrong. But CAT3 is the classification for the airports with most precise equipments, right?
CAT3 for more precise operations, yes.
So you mentioned some slides before that the requirement for auto landing is CAT2, right?
No, okay. I think even I did not speak about auto landing, but sorry for that. Let me check. It was written somewhere in the slide. Sorry, just let me.
Yes, this
Yeah,
one.
okay. Yes, this one. Okay. No, it's different. So one thing is more demanding operations like Autoland and Cat2. Yeah.
Okay. Okay. My fault.
Yeah.
Sorry.
Okay. Perhaps one other question.
I can do it. Okay, yeah, I think we have one more question. The last one before we go for lunch.
In the first slides where you show all the airports, in slide 10.
Okay.
Slide 10.
Thank you. Yes.
We can see in Spain, all the center of Spain, there has no airports, even the capital. Why is this?
Yes, because well, let me come back to one point.
You are in Torrejón de Ardoz, no?
In the very center, yes. Yes, it is.
So.
Let me, where it is. Okay, because we are usually, so as you can see here, navigation service provider are requested to do also a safety assessment. And we have a very exigent authority. That could be my excuse. So we will feel it. I can tell you, but and very soon would be the case. But still, well, it's true that we are missing. We don't have so many airports as in this area. We have not so many airports in Spain also, I would say, but we will fill it with little green aircraft. So this, if you go to the ESSP or EUSPA web, you could follow the progress, and you will see already where it is foreseen to deploy this, to implement this kind of operations. But yeah, and I was afraid to do this picture, so you saw it.
Okay. So it's good to do first these safety assessments before to deploy the
Yes.
safety of life service like EGNOS. Okay, so we are perfectly on time. It's 12 o'clock here, local time, 5 p.m. in Madrid. So I thank you very much for the talk. And this will be uploaded in the GIC website, so we can replay it later on. Thanks very much for participating in the masterclass, Javier.
Okay, thank you for the opportunity. Okay, thank you.
Okay, bye, goodbye.